Is this take one?
That's it. Just go for it.
Well,
Can I just say,
Andrew, and thanks, Mark. And I do apologize for that sojourn. For some reason, my audio and my video seem to be incompatible when everybody logged into Zoom, and my whole machine crashed. And I had to transfer files. I'm on my laptop now. So welcome to the talk. And it's about the speed of light and other stellar effects. Now, on this first screen, you see on the left there a photograph. That is a telescope. You may think it's a piece of drain pipe, but it's a telescope. And it's hanging on the wall at Greenwich in the observatory. And I took that photograph some years ago. Now, the owner of that telescope became rich and famous, not just once in his life, but twice. But before I introduce you to this gentleman, I need to set the stage onto which he walked. The first person in modern history to have a crack at getting the speed of light was Galileo. He had his fingers in every pie, and he was doing it by having lanterns, he himself and an accomplice, on two hills in Rome about a mile apart. And when he opened the shutters on his lantern, the other chap down the other side, when he saw the light, he would open the shutters on his lantern. And then when Galileo saw that light come back, he'd do a simple distance divided by time over distance, and he failed to actually get a speed of light because his conclusion was if it's not instantaneous, it's extraordinarily rapid. The second person to bump into light was a man by the name of Ollie Romer. He came from Denmark but was working in Paris at the time. And what Romer was doing was studying, I don't know whether you can see my I wanted to go back. I've gone forward one there. Sorry, I didn't think you could see my mouse. Romer was studying the orbit of Io, which is the innermost satellite of Jupiter. And in fact, Romer wasn't the only one. Everybody was studying it because this was helpful to Newton's situation. The period of it, which was about 1 3/4 days, enables you to get a fair bit of data in a reasonable time. And let me just show you a little demonstration of that. On this little demonstration down the bottom here, I have what we see of Jupiter. There's the 4 classic satellites, Jupiter. The white one here is Io. Now, when I start this running, this little simulation running, it stops automatically. I've got it stopping automatically under software control when Io is about to go behind Jupiter. And what astronomers like Romer were trying to do was to predict that moment in time. And it's kind of a Newtonian period. Now, if we look up the top here, what I've got up the top here is looking down on the orbits of the Earth and Jupiter now around the Sun. We see that on this particular pass, that Jupiter is nearly 6 times away from the Earth as it is from the Sun. So if I resume it now, and we'll see what happens when it comes around the next time. And when it comes around the next time, we'll see that we are less than 6 now. It's only 5 times the distance from the Sun. Now, Romer correctly deduced that the reason that they were having problems was because the speed of light was not infinite. Light didn't appear at your eyes instantaneously. And so it took a certain amount of time to come from Jupiter to the Earth. And Romer worked backwards from his data to try and get a result for that speed of light. And what he found was that the speed of light was 200,000 kilometers per second. It's only about 33% wrong. Modern historians have looked at exactly how he went about it, like historians and mathematicians, and his calculation was correct, but the radius of the Earth was not known to a good enough approximation to get a good answer. Nevertheless, Romer has become the first person in history to measure the speed of light and to prove that it is not infinite. So moving on now, I'm going to move away from light and now look at some other effects. The modern day starting point for astronomy was 1656, when Huygens invented the pendulum clock. Prior to that time, no clock could be put together that was better than 15 minutes in a whole day. But Huygens' clock, well, Huygens didn't make it. It was made the next year. Huygens was the designer. And the first clock that was made was accurate to about 15 seconds a day. So suddenly we have the capability of starting to measure the heavens. And by the time we get to 1675, when King Charles II sets up the Royal Observatory at Greenwich, clocks are already accurate to within a second a day. So the race is on. We can now study where all the stars are. And what King Charles II said to Flamsteed to do was to measure the places of the fixed stars, because this was very important to longitude, but I'm not going down the longitude route tonight. However, the race is on now. We're finding out what's up there. Now, here's another property of the Earth and its axis that has been known for thousands of years. As you can see, it was accurately estimated by Hipparchus in 130 BC using data that was going back a few hundred years. And that's generally thought to be one of the greatest discoveries in astronomy because he has such limited data. And you can see the gyroscope on the right there is showing us what the Earth's doing. But the Earth takes a bit longer than that. It's 26,000 years. So when people like Flamsteed got going, they knew that the stars were going to be moving, that they were not fixed, as in fixed. But they also knew roughly what precession was, and they could take account of it when they were doing their measurements. And I now want to show you a little stellar dynamics demonstration. What we're going to see on the screen here is a Mercator projection of all the stars out to about the 5th magnitude. And in the middle of the screen there, that's midday, that red line. The white line on the left there is the 0 of right ascension. And we can see that the sun is on midday. And I'm going to start this running now. And what we're going to see is I'm adding a day exactly, a solar day exactly, repeatedly. I mean, it goes through a whole year in about 12 seconds. Or that's what it does on my main machine, maybe a bit longer on this one. But you can see that the stars are moving inexorably when I do that because their day is about 4 minutes less than a solar day. And let me just pause that for a second. I'm going to zoom in on it now so we can see the behavior of the stars when we get right into them, because this is what the astronomers were going to be studying and discovering, you know, with their newfound clocks and telescopes. I'm going to zoom in on this red star because there's an awful lot of nothing there. If I zoom in and just randomly pick where the sun perhaps is now, we won't be seeing very much. But that red star happens to be Alpha Centauri. So I'm going to zoom in and I'll resume this and we'll start to zoom in. Right, so the stars are disappearing gradually now. I go in by a factor of 2 every time. Now, that white circle I'm drawing there, that is the size of the sun in the sky. So we can see what sort of movements we're seeing in that star as we zoom in. And you can see it's jiggling about a bit and it's moving inexorably off to the left. That moving off to the left, that is precession. That's the 26,000 year cycle, or the start thereof. But I've got a little checkbox down the bottom here and I can remove precession so we can study the star after we've removed precession. And we can see now it kind of stays in the center of the sun there. Let me zoom in a bit further. And we can see it's a double star, which it is, and they're moving in unison, but they are moving and the movement is quite small compared with the size of the sun, as you can see on that screen. We know that. I'm showing you an up-to-date mathematical model here, but at the beginning of the game, the astronomers didn't really know what they were shooting at, but they suspected they were shooting at small distant movements, even if they were shooting at movements. And onto the stage came Copernicus. We're going back 100 years now, and Copernicus was the heretic. He's the man that said, hang on, the sun is at the center of the universe and not the Earth. And of course, he got Galileo into trouble as well, because Galileo thought the same thing. But a side effect of Copernicus's pronouncement is that stellar parallax is a consequence. And I want to show you what stellar parallax is. It's, and again, another little demonstration here. I can't see part of the screen, but that doesn't matter. When I put this simulation on, what we're seeing is on the left of the screen there is a little simulation of the Earth going around the sun, because that's what Copernicus said was happening. Then we see a nearby star and we see a distant star. Now, as I simulate the Earth going around the sun, you can see that sometimes that distant star is to the south of the nearby star and sometimes to the north. That's parallax. And so if you wanted to measure parallax as an astronomer, you would go through a cycle of 1 year at least, watch the star going north, coming all the way down, going south, and then coming back to where it started from. So that's parallax. And because the astronomers realized this, and this was a holy grail, because if you could find parallax, you can prove Copernicus. But as with all astronomers, do not like the atmosphere. An atmosphere gets in the way of looking for stars and what they're doing, particularly for small movement. So let me show you that one now. I can't see the right-hand side at the moment, I'm afraid, because of some screens on there. But the atmosphere, there's a star coming in from the side here, which I can't see, from G, I think it is, to the atmosphere, and then it refracts in the atmosphere and comes down to a point on the ground. Oh, it comes from D, I think, and then it finishes at F on the ground. But you'll see that if you follow the line directly from F, the star appears to be at G, which is above D, where it starts. So in other words, whenever we look at a star in the night sky, we actually see it a little bit higher than it really is because of refraction. And refraction is largest at the horizon, and it's smallest at that point A there at the top, which is the zenith, coming straight through the atmosphere perpendicularly to the Earth. So if we're looking at the star at A, it doesn't move at all. But let me show you how bad the, I can't see my buttons actually to press to start this thing running. They're underneath the photo. Mark, can you take all the images off my screen momentarily? I've got a little simulation here, which I can't get to the button off.
I can't take anything off your Zoom,
okay.
I'm afraid.
Well, I'll just do it in words. What I was going to show you on the left there was the hidden piece, which was over here. The sun is behind this, and here's what we could see where the sun is on this one. And the simulation takes the sun up just below the horizon, but over here you can see the whole of the sun, which shows you how far it's being refracted at the horizon. Now, what this means is, if an astronomer set out to look for parallax, and the parallax was quite small, and it will be, otherwise we'd see the stars moving by quite some distance, if parallax was the size of the sun, for example, you wouldn't want to look at the horizon for a star to measure, because if the star itself is going to move by this much, and you're looking for this little tiny bit at the end, nobody's going to believe you. You are going to want to look at a star in the zenith, because it doesn't get moved by the atmosphere as it comes down to us. And I can't even get out of this now. I can't get out of it, Mark. Oh gosh. No, I can probably do it this way. Yeah,
I think
so that's
next to your view options, Bruce.
Yeah.
Next to your view options, there might be some options to hide the floating toolbar.
So I've got participants. Will I turn them off? Oh, they're behind something. Let's just press on for the moment. Okay. Although it gets a bit hefty fairly soon. Now that's atmospheric interference. And so what we've discovered there is, if we want to look for a small, minute movement of a star, the best place to look is the zenith. And there is a star, if you live in London, called Gamma Draconis, which is often called the zenith star. And it's this star here called Eterman. That star comes overhead London every day and twice on one day of the year, because the sidereal year is 366 days. So Robert Hooke was the first man in history to put all those little components I've shown you together in 1669. And he invented the world's first zenith telescope. It's a telescope that's going to hang vertically, basically. That's all there is to it. Now, and you need to make that telescope move north and south at its bottom end, so you can follow the star as it goes north-south. You cannot measure the east-west distance, because you need a clock to measure that, because right ascension is related to time. So it's only the north-south direction that you can measure. And so Hooke rigged this up, and you can see there's an object lens up the top here, right, and then a part of a tube down there, and he drilled a hole in the floor here, and he went down two floors, and he had an eyepiece down here. So what did he do? Well, he actually got pretty excited. He measured Gamma Draconis 4 times between early July and late October 1669, and it moved at least 1/100th of a degree, and he was ecstatic. He's got parallax. Now, Hooke wasn't stupid. You don't have parallax until you measure at least for a year and see the whole cycle. So it was a case of, hang on, you got to do more than that. Now, as I say, Hooke wasn't stupid. So why didn't he measure for a year? Well, we know historically that he broke his object lens The date is unknown, but I suspect it was after he took the fourth measurement. So Hooke was kind of stymied there, but he wasn't finished. Robert Hooke, after the Great Fire, 1666, was the city surveyor, and he was responsible for helping to rebuild the city. And if you think that it was Sir Christopher Wren, he was the royal surveyor. So the pair of them worked together, and they had been pals at university anyway. But Hooke made the design for this particular object, which is the monument to the Great Fire, entirely of his own hand. And if we look inside it, if you pop your head around the door and you look inside, you can see that it's hollow. So all the stairs going up the outside, they're attached to the inside of the column. And there's a little white dot down at the end here. That's a perspex, a piece of perspex these days. Used to be a wooden trapdoor the Hooke could open, because this is a Zenith telescope. And Hooke had this built to finish off the job that he didn't finish off in Gresham College. Unfortunately, then as now, the traffic of London was a bit of a nuisance, and it caused the monument to vibrate slightly, and he was unable to make any measurements. So Hooke was now out of the picture. Next person to come on the scene, Flamsteed, first astronomer royal. A couple of years later, he had a 100-foot well over to the right here on the premises, which is roughly here according to Greenwich, mightn't be in the right place. And so he built a Zenith telescope into a 100-foot well. Now it's recorded in history that he didn't like the cold damp down the bottom there, so he gave the job up. But what's more likely is the object lens has survived to this day. He only made one measurement, and he probably realized that he was up against it, because that object lens is known to be extremely poor in quality. Now things go quiet for 45 years. I'd still like to get this screen. Do I click the participants bit or something?
If you can look under view options, there might be something to hide the floating controls.
Yeah.
Bruce, is it the picture with all the people on that's the problem?
Hide video panel. Wait a minute. Hide floating meeting controls.
Yes, hide that one. Yes, hide floating meeting controls. That'll help.
No, they're still there. So, all right, let's see what happens next. So onto the stage after that 45 years comes the man that we're all looking for. His name is James Bradley, and he was the owner of that telescope. And I want to tell you something now about this man. He was born in 1692 in Gloucestershire in a place called Sherborne. He entered Balliol College in Oxford in 1711, got a BA and an MA by 1717, but this was not astronomy, it was divinity. And he became a minister. He was ordained in 1719 and became the rector of Bridstow in Monmouthshire. Not a lot of astronomy there, but he was leading a double life because he had an uncle who lived in Wanstead in London, and his uncle was an exceptionally accomplished astronomer. In fact, James Pound at this point in history was probably the best observational astronomer in the world. He certainly was in this country. And we know that James Bradley was visiting Pound because from 1715 onwards, Bradley's handwriting appears in all of the, a lot of the observations. So he was going up and down and seeing Pound. And Pound was being asked by various important people to do measurements for them, for their theories. In 1716 there, Halley did. That wasn't for comets, by the way, that was just for solar system measurements. And even the great Isaac Newton himself came on the scene in 1719 to 20. He knew Pound quite well, and he paid Pound and Bradley to make observations for his theories. Now, interestingly, by the way, the contract for that for 1719 to 20 was actually a contract for the pair of them, and not Pound with Bradley helping him. So Bradley must have been becoming very good by this time. And incidentally, at that point in time, the pair of them probably were the best two observational astronomers in the world. 1721, the professor of astronomy at Oxford dies, and Oxford University comes looking for Pound. But Pound's very happy with his lot, by the way. He's got his astronomical observatory all set up. He's got his flock that he tends to. And in fact, I don't think Oxford actually had an observatory. So Pound, he didn't want to have anything to do with it. Whereupon they asked Bradley if he wanted to do the job, and Bradley accepted it. Now, the rules of the game were he had to leave his job in Bridstow, which he did, and he came east, but he didn't go to Oxford. He came and lived in Wanstead, only traveling to Oxford when he had to give lectures, etc. And I suspect that's for the same reason that Pound turned it down. The observatory was in Wanstead, and it was a really good one, and it was run by Pound. Unfortunately for Bradley, death takes a hand. In 1724, James Pound died. He was only 55 years of age at this point, and Bradley was absolutely devastated. I think in this day and age, we'd say he was depressed. But Pound and Bradley already had a pal over in Kew Gardens, lived in a big mansion, whom they'd been doing some friendly work with before. And this pal was an amateur astronomer, and his name was Samuel Molyneux. And he lived in this wonderful mansion, but at the time that Molyneux was living in it, only the middle bit was in existence. The rest was added later. Molyneux actually was very ambitious. He wanted to have his name in astronomy for doing something. He was, in fact, by the way, at this point in time, an MP at Westminster. And you'll never guess what he picked out. He picked out finishing off what Hooke started. And Bradley was quite keen once he came on board. So this was helping Bradley to come out of his depression. And they went to a chap called George Graham and asked him to build a 24-foot Zenith telescope that they were going to put on one of the chimneys at the mansion, and they were going to study the parallax of Gamma Draconis. Now, just pause and mention George Graham. If you ever do any research going back in time, George Graham is one of the big names, and he made excellent clocks, but he also made telescopes. Anyway, Bradley and Molyneux made their first observation on the 3rd of December, 1725. And I want to show you what they saw if I can get to the button. Oh, I can, thank God. Thank goodness for that. When I press the simulate button here, watch the blue square on the top left, and you're going to see two lines, one navy blue and one green. The green one is what the star did, and the navy blue one is what the star would have done if this was parallax. So there we go. And it runs this for a year because that's when they took stock after this 1 year. Bradley and Molyneux, this is exactly what the star did. You'll notice it's a bit skew-iffy. It doesn't come back to where it started from. But the blue ellipse looks pretty good, and that's parallax. Bradley worked that out mathematically. But they could only see this green line here, because remember, they aren't measuring the east-west direction. That's a clock, that's time. This one is the one that goes up and down in distance, and so they only measured this green line here. But it's nice, it goes up and comes back to where it started from. But if we look at these two graphs over on the right now, they could plot the distance of this star from its center position with date. And as you can see, they get a lovely sine curve up here and another one down here. But they don't superimpose. There's a difference between them. This is not parallax. The experiment has failed. But they have got a pretty good second prize, because whenever you see a sine curve in nature, there's going to be a theory. Okay. Oh, incidentally, the star moved 19.7 seconds of arc north and 19.6 south, and the whole distance is about 2% of the diameter of the sun. So you can see what size they were looking at here. So Bradley takes stock. They're 1 year in, and they've just failed to see parallax. The Zenith telescope, right, that they're using can only move by a very small amount at the bottom end, because all they were interested in was Gamma Draconis when they went to George Graham to get him to make it. And it can only move 7 to 8 minutes of arc at the bottom. And all they could see with that telescope was two stars, the Gamma Draconis that they're aiming at, and another smaller star about 10 hours of right ascension away from it. Not good, because Bradley realizes that if you're going to come up with a theory for something like they've seen, you're going to have to make sure that it's not the only star that does it. Otherwise, you won't be believed. So he wants to look at many stars. And he decides that if he gets an arc movement of 6.25 degrees at the bottom of the telescope, that's a bit more, right? You're still not getting into the realms of having bad news with refraction, but he could see over 100 stars. And he wanted to have 1/10 of a second of arc of positional accuracy in that telescope. So there, he gives well over. So he goes back to George Graham, and this time he says, please build me a 12-foot Zenith telescope, because he is going to put it at Wanstead. Now, you might think that poor old Samuel Molyneux is getting a bit of a kick here, but in the first year, when they were just looking at Gamma Draconis, of course, he could travel to Kew as and when he knew the star was going to be there, and at other times, I'm sure that Molyneux actually did the measurements. So it was more casual sort of work. But what he wants to do now is to measure dozens of stars. He went on to measure around 35 stars a lot, and about 20 more a bit, shall we say, to check that all stars were doing this. So that's why he wants it at Wanstead. He doesn't want to go and live at Kew, but he can't go backwards and forwards like a yo-yo to measure that many stars. And I think Molyneux bought into it all right, because at this point in time, Molyneux was on a secondment to the Admiralty, so he wasn't living at home. And here's the Zenith telescope that George Graham built for him, the one that I showed earlier, and there's a bit of detail at the bottom here. And he commissioned that telescope on the 19th of August, 1727, and started making all the measurements now in his aunt's house in Wanstead. Unfortunately, death takes a turn again. Sadly, in April 1728, Molyneux was attending the Houses of Parliament and he collapsed. He was taken home, but about 2 to 3 days later, he died, aged only 38. And if you're anything like me and you go looking for places where things are, like the White House, that was the name of that mansion that he lived in. I went and visited Kew Gardens, paid all my monies to get in, etc., etc. And all I could find was a little plaque on the ground that said, this is where the White House was. Heaven knows where the telescope is. So if you want to go to Kew Gardens, a nice place to go to, but don't expect to see the White House. But this particular death was very sad, actually, because Bradley, although he didn't know it at the time, was less than 6 months away from making the biggest discovery of all time in the field of celestial dynamics. And it's a story a bit like Newton. On the left there we see Newton. We all know the story about the apple falling, and he's pondering it, and he gets his theories of gravity. With Bradley, it's a yacht. And this comes from Bradley's mouth, by the way. Nobody has made this up after he died. He was invited by a friend of his to have a little sail up and down the Thames on a Sunday afternoon with a group of other people in his yacht. He accepted. He went on this jolly on the yacht. And he noticed that sometimes the pennant at the top here moved slightly. And he said to his friend, is the wind changing direction, you know, a little bit all the time? And his friend said, no, the wind's constant. That is changing only when I alter the direction of the yacht. Well, this set Bradley thinking. Bradley does some what ifs now. He says, what if I replace the constant wind with the constant starlight? What if I replace the yacht with the Earth, which is a moving object in the same way as the yacht is? And what if I replace the pennant with the telescope? And you have to adjust the telescope slightly as the Earth moves and turns. Now, the very interesting step that he made there was the Earth moving and turning, because to prove parallax, it's only positional. You know, the Earth's in a particular place and the rays come directly from the stars and you can see whether it's north or south, the other star. This is an effect that occurs because the Earth is actually moving and changing direction. That was the key thing that he added to it. And here's a way, it's called the aberration of light, and here's how you'll pick it up from the web if you want to look at it. If you're standing still in a rainstorm and there's no wind and it's falling vertically, you hold an umbrella like this. If you start running forwards, as we all know, you have to hold the umbrella like that so you don't get hit by the rain. If you could put a telescope on a totally stationary platform, you would point it at the stars. But there isn't a totally stationary platform. We're on a moving Earth. And because the Earth is moving, in the same way as you have to tilt the umbrella here and the pennant on the yacht change slightly, you have to bend it over to see the light of the star. And here are the results that Bradley got. If we look over here to the right first, this is just a vector triangle with the velocity of light here, perpendicular to the velocity of the Earth. And I've done it deliberately perpendicular to the velocity of the Earth, because that's the biggest angle you ever have to move the telescope. It's moved by smaller amounts when it's not perpendicular. And that angle is called kappa, and it's called the constant of aberration, because the biggest angle is called the constant of aberration. He measured kappa as 22.2 seconds of arc with this experiment. Today's value, which I got off the NASA website, 20.49552. He's only 0.3 out in 200, but in 20, 3 in 200, 1.5%. He can get C over V all right, because it's the arc tangent of kappa. He got to 10,210, and the answer is 10,064. And he could also work out the average time for light from the sun to reach the Earth, 8 minutes, 12 seconds. And it's now 8 minutes, measured at 8 minutes, 19. And remember, this is all done in 1729. Error from today's values. Now, he didn't publish the speed of light. And I think he did that deliberately, because the speed of light is a function of the radius of the Earth around the sun. And that's a number he decided, I would think, wasn't known to a good enough accuracy. So he published what he knew to be accurate and measured. And I've gone back in history and I've tried to find out what the radius of the Earth was at his time. And I think it's about 7% wrong. So to get V there, the velocity of the Earth, you do 2 pi times the radius of the Earth, and you divide that by 365.25 and get the appropriate units. If he had done that calculation, he'd have been about 5.5% wrong, because the 7% inaccuracy in the Earth's radius is opposite to the 1.5 error he had. So he'd be known as the person that measured light to within 5.5%. But he's got away with 1.5, in my opinion, because he decided that he'd better wait till somebody knew what the radius of the Earth was. So in summary here, Bradley and Molyneux have set out to find the parallax of Gamma Draconis, but instead, Bradley has become the first person in history to measure the speed of light to within 1.5%, which is absolutely stunning, in my opinion, 1729. Now, and he didn't even know he was looking for it. But Bradley's not finished. I'm going to show you more of his observations now. And I hope I've got the buttons this time, or just. Right, I've got 3 boxes now with thrown away parallax. You're not going to see it. I'm only going to draw green lines, and I'm going to draw 3 of them. I'm going to show you what the star actually does up here, a full simulation of the star. I'm going to show you down here what the star is doing when we subtract aberration from it, because we know about aberration now. And I'm going to show you up here what Bradley saw. Oh, my goodness, I pressed the wrong button. Simulate. Right, so I'm going to show you the first 3 years, first of all, because that's when he made his significant decision. And there's the first 3 years. He now knows the aberration of light. So that's what the star did in the first 3 years. You'll notice it doesn't come back to where it started from, and it's kind of spreading itself out here. Here's the difference between that and the aberration, which he's already measured. That's the difference. And he knows that there's something down there because he's seen this line take a move upwards to the north. And he knows that aberration is only related to the length of the line. So all these lengths are approximately the same. It depends on what date I selected to start it. They don't look quite the same length, but I'm plotting these things just from date to date, and he would have been looking at it more carefully. But you can see that that line is moving upwards. So in 1729, when he's going into print, and he became rich and famous instantly, by the way, because everybody wanted to hear Dr. Bradley give talks, and they paid money for him to give talks, and he got enough money to buy a house in Oxford in about 1832, which I'll come on to a bit and again shortly. But Bradley has seen this movement, and he's going to keep going. So let me resume it. And we'll take another 3 years out of it now, or 4, I think. So we can see the pattern coming up now. We can see quite a nice pattern down the bottom here. You know, it looks pretty good. We can see a pattern here, and we can see a very significant pattern here now. So he was right and proper to continue. And the reason I stopped it at 1733 was he just about had a heart attack at this point, because his aunt, sometime in 1732, decides she wants to sell the house and come and live with him in Oxford. She's got a son, John Bradley, whom I think also went into astronomy with James at one point, and she wants to bring her son up to Oxford as well. Well, Bradley's got his telescope well and truly strapped to that chimney, and he's not going to take it off, because he'd have to start from scratch again, because he wouldn't have exactly the same positioning, and he's a very careful worker. However, it was a woman that was buying the house. Bradley must have been a bit of a charmer, so he went to the woman and he said, "Look, would it be all right if I left my telescope on this chimney and came in anytime, day or night, and did some measurements?" And she said, "Yeah, it's fine, Mr. Bradley. You know, you can do that." So he got past that point. Let's resume it again. Just while it's going to go for a few years now, just while it's doing that, if you can see where I've got the mouse, there's a little red dot here in the middle. If you look up a stellar atlas for the coordinates of Gamma Draconis, that's where it'll tell you where Gamma Draconis is. And we can see it never even goes there, because you're supposed to know the corrections that you make to that point to get to the exact position of the star. Right, we've now hit 1742. Death takes a hand again. This time it was the second Astronomer Royal at Greenwich. He died in January 1742. Edmund Halley is his name. And the government indicated that it was going to put out an advertisement and ask astronomers to apply for this position, this vacant position. But there was a riot. Not a physical riot, just a verbal riot, because the whole country went up in arms. You know, you can't give anybody but Bradley this job. He'll be a laughing stock. He's the best astronomer in the world. And I think the government saw the sense of that, and they offered Bradley the job, and he took it. So from 1742 on, he kept the professorship at Oxford, incidentally, but from 1742 on, he's now back in London, and he can get to Wanstead quite easily. So let's just tidy this up and get to the end now. You can see the whole pattern developing. Bradley could see the pattern developing. He knew for many years before this finished what he was shooting at, but he was not going to give up until he had all the data. He was a very careful worker. So he's waited until that vertical line comes back to where it started from. We can see this is joined up quite nicely, and we can see a fairly nice pattern here. I ran it an extra year or two, which is why there's a bit of extra lines here. Bradley knew from fairly early on that this was going to be a gravitational situation. And to boot, the moon has a force on the Earth as it spins on its axis and goes around the sun. And that effect is an 18.6 year period. And so that's what he's found, an 18.6 year period. And let me just show you what that lunar orbit is now, where this comes from. The ecliptic is horizontal here. The moon's orbit is here. It's about 5.5 degrees inclined to the ecliptic. And let's pick it up here at this node here, the rising node. The moon goes up here 5.5 degrees above the ecliptic, dives down here to the descending node, comes back around again, but it doesn't come back to where it started. It comes back a little bit further back on the ecliptic. It's called the retrograde motion, and it's got a period of 18.6 years. It goes here 1 year, here, goes all the way around and comes back to where it starts from, 18.6 years. And this gives rise to something called nutation, which is a wobble in the Earth's axis. If we look at the diagram on the left here, there's the Earth with its axis. It's going around for 26,000 years in precession, but as it does that, it wobbles. And it wobbles by the amounts shown in this ellipse, which you saw my maths develop in the previous slide. The 18.6 year cycle is the ellipse itself. The little curly bits on it, because the sun And the large planets like Jupiter and Saturn have an effect as well. A lot less than the moon because they're a bit further away, but that's what causes the little curly loops. So Bradley has now become famous again and rich again, twice with the same telescope. He went into print in 1748. So let me just summarize what we've learned here about the position of a star. Firstly, the position of a star is affected by the Earth's atmosphere. We can't look at small motions of stars other than at the zenith if we're on planet Earth. It's different for the Hubble telescope. We've learned about precession of the Earth's axis. The stars move inexorably on a cycle of 26,000 years. We've learned about the nutation of the Earth's axis, thanks to Bradley. We've learned about the aberration of light, thanks to Bradley. We set out looking for stellar parallax, but didn't find it. And this is quite interesting, actually, because in fact, Bradley's measurement of the aberration of light, because it requires a moving Earth, that proves Copernicus. That's fine. So Copernicus is fine once he's proved the aberration of light. So you don't need stellar parallax, but we need stellar parallax for something else, and that's the size of the universe. If we can't measure the distance to any star in the sky there, then we can't get a handle on how big the universe is and where other stars are, etc. And it wasn't until 1838 that was found. Now, that would be a subject for another talk, so I won't go any further into it now. Likewise for the last one, which is still a proper motion, that the fact of the matter is that no star out there is physically stationary compared with the Earth. They're all moving in different directions. Some of the movement is towards and away from us. We won't see that with a telescope. We see it with redshift, for example. But when coming across the path of the Earth, then we would see that as a proper motion. And Bradley was lucky because Gamma Draconis doesn't have any stellar parallax. It's 150 light years away. Well, it does have it, but it's very tiny. And it's not moving very fast either as a stellar proper motion. But Bradley did quote in his papers that if anything had a stellar parallax up to about 1 second of arc, he'd have been able to sort the thing out. So he'd have been looking for 3 things then in his data, but he claims he would have sorted it out. So Bradley wasn't a one-man band or even a two-man band. He did loads of things. Some of these he did with Pound, and I haven't even listed the lot here, but just let me draw your attention to the bottom 2 here. There's an interesting story about these in some respects. Number 9 here, proper equipment installed in Greenwich. Well, he was the 3rd Astronomer Royal. The 1st Astronomer Royal was Flamsteed, and guess what? The government didn't give Flamsteed any money to buy equipment. So Flamsteed had to buy it himself out of his salary. And when he died, his wife just picked it all up and walked off with it. So there's nothing there. And so when poor old Halley came in, he had to buy some new equipment. But Halley actually had an Achilles heel as well. He had no idea how to keep the equipment in good condition. So when Bradley appeared, the stuff was in bad condition. So he went off to the government and he said, "Could you give me £1,000? I want to do this properly." And they said, "Yeah, we'll give you £1,000. And the first thing he did was to buy his own telescope for 45 quid and put it at Greenwich. But it was used until 1839, so it wasn't just a complete swizzle. But the other interesting thing is down here, number 10, he made over 60,000 transit and quadrant observations. They're the observations you need to make stellar atlases. And interestingly, by the time he got Greenwich all sorted out, he only did that for about 10 years before his health started to decline. And our 1st Astronomer Royal in Edinburgh, Thomas Henderson, also only had a 10-year stint because he died suddenly in his early 40s. And he also did 60,000 measurements in a 10-year period. So I think we can be perfectly happy that our 1st Astronomer Royal was right up there with the best. So how's history treated James Bradley? I mean, he was known by everybody when he did the business. But he's not a household name today, is he? And I'll bet some of you people out there, like me, before I started doing this, knew his name, but had absolutely no idea what his place in history was. And he does get treated a bit poorly, actually, when you think about it. I don't know whether they've changed it now, but the Royal Observatory of Greenwich, you know, it's now a museum. They quote that this telescope, this is on their website, it's one of the most important instruments on display. Well, hell's teeth. I mean, it just looks like a drain pipe and a grey wall. I've said to them when I've been down there, you've got to dress this up. People have got to see that this is really something. Oh, they may have. It's a few years since I took that photograph. His house. Well, it's not his house. This is where I did the pilgrimage out to Wanstead. You're on a Central Line train for ages, but you eventually get there. That's a rebuild. That's not the house he lived in, but there's a green plaque on it. You know, Bradley lived here. There's the green plaque. Now, they could put just about anything on that green plaque, but what have they put on it? First person to demonstrate that the Earth moves around the sun. I mean, that's Dullsville. That's just a side effect. So nobody's really jumping up and down. Here's his grave, which is in Minchinhampton, Gloucestershire. He went back to Gloucestershire when his health was failing, and that's where he died. This is the totality of his monument, and on the end, this is what it reads: to the memory of the Reverend James Bradley, D.D., 1693 to 1762, Astronomer Royal, 1742 to 1762. But he has got at least one fan, Sir George Biddle Airy. And Airy said the following: Gamma Draconis is the birth star of modern astronomy. And I don't think we'd want to argue against that. And I can assure you, he has got another fan, me. I think this guy is one of the best people that I've done research on. He was a joy to do research on, and he's a fabulous man in what he did. Thank you.
Thank you, Bruce. That was great. Our president's disappeared.
No, is that what the hiatus was?
Thank you. That was really fascinating. Here he is.
My internet died 3 times, sadly. Yes, I'm ever so sorry. My internet dropped out about 3 times. But a cracking talk, Bruce. Thank you very much indeed.
Thank you.
Thank you very much.
Questions, Peter? Did any come through?
No, I think it was so comprehensive that nobody's asked any questions. I don't know if there's any out on YouTube. Is there? We can ask for questions now.
Can I ask a question, please? Why do you think Bradley isn't better known, Bruce?
I don't know. One of the things that I realized when I started doing research, you know, on astronomy years ago, 10 years ago or so ago, one of the things I realized is I'd never been taught at school how to measure the speed of light. You know, you're told about the speed. I'm talking physics here. Some of you may not have done physics, but you got told about the speed of sound and all sorts of things, but no one ever mentioned. And I didn't really realize until I started doing some of these investigations how little I knew about light and how you measured its speed. And the interesting thing was its speed was measured by somebody who wasn't even looking at it, looking for it.
Amazing. Thank you.
Could I just ask a quick or make a quick comment about Hooke's telescope at the monument?
Mm-hmm.
Couple of things that I actually wrote a bit about it for another local astronomical society down this way. Couple of things I found out was one of the problems he had problems with the cooling of his telescope tube because it's actually built of stone. The sun heated the south side of it, and of course it bent.
Mm-hmm.
And obviously took rather more than a day or more than a night to cool down. So it was continually moving, which is another reason he never actually got any sensible measurements out of it.
Yeah, that's great, John, because I didn't read that, but where I did my research told me the bit about the traffic, you know, causing it. But I think what you're saying there is actually a better reason.
Yes. The other thing that it wasn't only designed as a Zenith telescope. Apparently the steps are all 12 inches high. So he could actually carry out experiments like dropping things and pendulum experiments which apparently
Exactly.
before.
Actually, I think they're 6 inches high, but I
Yes.
didn't say that because we'd lost a lot of time at the beginning. And I was
Yes.
trying to actually. But
Before
you're
that,
absolutely right.
before
He
that,
was
they
going to
used,
do some experimentations with the precision that he built those steps.
yes. Before that, they used St Paul's Cathedral apparently, and that got a bit
Mhm.
awkward with big pendulums and things.
By the way, Hooke was a genuine polymath.
Yes.
You know, our bodies, if you do biology, our bodies are made of cells, right?
Yep.
The first person in history to call themselves was Hooke.
Yep.
So, I mean, Hooke's a very fascinating person to study. And it's so sad that he and Newton fell out, and Newton tried to write him out of history.
Yes, that's right. So there's no
Mm.
photographs of him, are there?
Yeah,
So, or paintings, as they would have been in those days.
yeah,
Newton had them all destroyed, I believe, as you said.
that's right. I believe that there's no known portrait of him because of Newton. Yeah.
Yes, and a lot of his books were they bought up by Newton or something and hidden or something, or because a lot of them only came out after Newton's death, didn't they?
Yeah, because there was the other argument between them because Hooke, before Newton, came up with the 3 laws of motion, slightly
Yes.
differently phrased. And Newton took them over, and Hooke was really angry when Newton didn't refer to him in the papers that he wrote about
Yes,
it.
yes, that's right.
And I think Newton used to say, oh, he couldn't do the maths.
Yes.
So that was
He
the riposte that he got from Newton.
Yeah, it's probably not that much astronomy, but you could do another presentation on Hooke. As I say, he needs a bit of up publicity as well, I think.
Yeah, he's a fascinating person.
Mm.
We've heard a lot about the second Astronomer Royal for Scotland, Piazzi Smythe, but we don't hear much about Henderson, do we, Bruce? So I don't know if he's one of the people you've researched. Maybe
I
he
wasn't
will be
going
someone
to
you talk
say
about.
any. Let me go back a couple of slides here. It's nearly at the end where I've got the 6. There we go. Strangely, I was thinking of saying this, but I thought, let's just keep quiet about this. Right. Everybody knows that. That comes from Hipparchus. These 2 come from Bradley. And then we got the last 2 here. And sadly, Edinburgh nearly got both of them. Henderson had the first measurements of stellar parallax ever taken in the early 1830s. And he knew it was parallax, but he had a slightly flawed instrument. And so he didn't want to go into print because not that many years earlier, somebody in Ireland, and I'll remember his name shortly, had gone into print and it was wrong and it ruined his whole career. So Henderson, being very conservative anyway, held on to his data and asked another person who replaced him where he'd done the measurements and got a new instrument as well, asked him to redo it. But in the meantime, Bessel in Germany stole the march. He got his Bessel's data is probably about 5 to 6 years after Henderson's, but Henderson hadn't published because he was conservative and wanted to be absolutely sure he had it right. But as soon as Bessel went into print, he did as well because he knew he must be right. But Bessel's in the history books. So we missed that one by a gnat's whisker. Number 6, stellar proper motion. When the second Astronomer Royal, whose name eludes me, I think you said it, Piazzi Smythe, yeah. When he came to Edinburgh, Astronomer Royals kind of have a project that they're going to do. And what Piazzi Smythe said was, I'm going to measure the apex of the sun's motion. Now that's the point in the universe that we're traveling towards. The sun is traveling towards and we're going with it. And the way to find that is to get stellar proper motions and work backwards from them to find which stars you're going past and which ones you're going towards and which ones you're going away from. And that was what he wanted to do. Now, the last 16 years he was on Carlton Hill, he published volumes 14 and 15 of the astronomical observations. And those 2 volumes have got just under 4,000 stars with their proper motions. But he didn't solve the apex of the sun's motion. And he stopped that, I think, when he left. Well, I don't know whether he stopped it working on it, but he stopped doing the measurements in about 1888 when he left Carlton Hill. He lived for another 12 years in Yorkshire and died in just early 1900. It was 1905 that someone cracked that from about 5,000 or 6,000 stars, but I'll bet they had Piazzi Smythe's data. And I would suspect, by the way, and I can't say this for certain, I would suspect that is the very first fulsome stellar proper motion study that was ever done. So Edinburgh in 5 and 6 there came into second place twice.
Or maybe you'd like to put the record straight on Thomas Henderson, certainly at some point.
Yeah, well, I can. I do a Henderson talk. Henderson is a difficult man to do a talk for because he died so young that there's not an awful lot of data. I have done a 1 hour talk on him though, but what I did in that 1 hour talk was to introduce the audience to more of that celestial dynamics that I show you, because I wanted to show what Henderson was up to. So I padded it out a bit. Oh, there's a really nice one. There's some nice experiments that Henderson got involved in that can add. I can do a talk on Henderson.
Okay, it's John here. Could I just say there's one more thing you need to add to your position of a star, which is bending by the gravitational field of the planets.
Oh, ouch. Well, you got me there. Yeah, well done.
It's very small, and in fact, I didn't realise that. Of course, Gaia doing its survey, they've actually got a complete model of where all the planets are, because they have to allow for that in the measurement of positions that Gaia takes when it measures something near a planet, in the sort of micro arc second sort of area. But obviously,
good point. I got this from a book that was written, prior to the sort of thing that you're talking about.
Yes.
Because you go into a library and you find this sort of stuff, in older books.
I only found that on the Gaia website when I was looking for something completely different.
Yeah.
Because I've been giving a talk on gravitational lensing and things. And it's quite nice. If you have a hunt around the Gaia website, there's a quite nice animation showing what happens as the planets go round and how much the stars therefore move. It's only a model rather than the actual measurements, but it's quite interesting. I didn't never realise you had to consider that when you wanted to do parallax measurements.
Yeah. No, that would bring it up to date.
Okay, thank you for that. I'm not sure whether Andrew's made it back or not, but we'll carry on. Are there any more questions? Maybe we should be stopping there anyway because of the Crew Dragon launch anyway. Hugh will be hanging around too much longer.
36 minutes, it just said.
Yeah, but they're starting to get dramatic. They're starting to fuel up.
Oh, right. It's very cloudy there, just like it is here.
Yeah. So can we all say a special thank you to Bruce yet again? That was really good, Bruce. Thank you. Very comprehensive. Thank you.
Thank you very much, Bruce. That's fantastic.
Thanks very much.
Thank you.
Thank you.
Yeah.
Just a reminder that we have this ASC showing of Residence Above the Clouds, which is about the second astronomer Royal Piazzi Smythe on Friday. That is sadly for members only because of copyright reasons, but we have more meetings next week and all the details on our website. We will have another talk from Bruce in June, I believe. We'll make sure all the technical issues are sorted out by then.
Well, I'll just use my laptop. I think there must be an incompatibility. I've had that webcam for some years now. There must be an incompatibility.
Yeah, it could be. Yeah. But thank you very much. And hope that everyone enjoys the launch tonight.
Thank you.
Okay.